Hello and welcome to this video on conservation of energy. Specifically, we're going to be talking about slightly more complex problems and tying in conservation of energy into previous units. This video is only required for AP students, but if you want to watch it on your own time, be my guest. One of the big ideas, one of the big struggles of students with the AP exam is integrating various different pieces of information. We know X, we know Y, but putting them together is very difficult. This problem was used in the previous video to demonstrate how a ball would move through the air, and we talked about how at the top wouldn't completely stop moving. We've seen this in projectile motions. It would have a velocity, but only in the x direction. Effectively, it's traveling that way. At the instant it's at the top. And I said we would talk about how to calculate how high up it is or how to work with that later. That's what we're doing today. The idea behind this is that we can solve problems in multiple steps, integrate them in many different forms. In order to find how high up this is, this delta y or h, whatever you prefer, we need to know how fast it's leaving the barrel at. At that point, we can go back and treat it like a projectile problem or an energy problem. So let's start there. Originally, the ball was compressed 0.12 meters. Spring constant 475, mass of 350. The question is, how fast is it leaving when it comes out of the ball? Well, we assume that the energy is completely transferred. In other words, E initial equals E final. And that the initial energy is 1/2 kx squared, and that's equal to 1/2 mv squared. Let's rewrite that so it's a little less messy. I can solve for the v, no problem. I'll go ahead and do that right now. And I'll get 4.42 meters per second. And that is my initial velocity it leaves the cannon at. If you remember, the final velocity that we had here at 0.2 matches that value, which makes sense. It's at the same height, will have the same velocity. We remember that from our range problems. From here, we have two options for solving how far up it goes. We could do it like a projectile motion problem. Find Vy initial, knowing that Vy final is going to be 0, and my acceleration is negative 9.8 meters per second squared, and find delta y. That's totally viable. But what I would rather do is go about it a slightly different way. Let's take this V initial, set it off to the side. And instead look at it like an energy problem. Because my energy here will equal my energy at the top. E initial equals E final. And the 1/2 kx squared will equal my mgh plus my 1/2 mv squared. I know the mass, I know g, and I'm looking for h. All I need to know is this v. And whereas with solving it as a projectile problem, I would go through and solve for my vy, instead of what I'm going to do is I'm going to solve for my v initial x. Why? Because I know from my projectile motion unit that the velocity in the x direction doesn't change, and at the top it's only moving in the x direction. So if I can find my v initial x, it'll be the same as my v x up here, which will just be my v. It's the only direction it's moving, and then I can solve the rest of the way through. It's a right triangle with a 35-degree angle, so I can find my v initial x that way using cosine. And get a value of 3.62 meters per second. From there, all I need to do is solve for h, and that'll tell me how high up it goes. It's a straightforward process at this point. Move the 1/2 mv squared to the other side, divide mg to the other side, and plug in my numbers. I'll get a number out of this, but I want to talk about the idea here. The fact that I couldn't solve this problem strictly by energy doesn't mean it's unsolvable, it just means that I need to dig into my repertoire of tricks and start solving it this other ways. And that is the higher level skills that are necessary for the AP exam and to do well in life and physics as a whole. The number for reference, by the way, is 0.38 meters. And this process, again, is the kind of idea that we're running into. But it's hard. It's a struggle. This idea takes some skill and getting used to. So I'm going to set you up with a practice problem and walk you through it, or at least give you some hints, and then have the answer broken into two parts. I like roller coasters a lot, in case you haven't figured it out. One of the things I once considered doing with my life is roller coaster design. Now, imagine a roller coaster goes down the hill, goes through the loop, and comes out the other side. What I want to know is how high the roller coaster needs to be, this 2,500 kilogram cart needs to be to make it through the loop at minimum. Right off the bat, this seems like an energy conservation problem. I know right at the top here, I'm going to have some amount of EG. And I know at the top here, I'm going to have some amount of EG because I'm still above the ground. But I also need to have some EK. And I know the height here. I can find it via the circle. I know the mass of the cart. I know G. The only problem is I don't know the velocity. Crud, okay, how do I find the velocity is the question that inevitably gets asked. Well, because this is moving in a circle, it's a circular shape no matter how poorly I draw it. I know that moving in a circle requires a certain velocity, requires a certain force. I can look at the sum of all forces in the y direction. I can label my forces, find my forces. If I'm looking for the minimum value, it'll be just equal to force gravity. And because I'm moving in my circle, I know the acceleration. The answer to this is broken up into two parts. The first is just finding the velocity and how to do that. Quick refresher. The second is finding the height once you've found the velocity. The pause will be in two segments. So feel free to check your answer after the first one or check both after you're done with them. But do make sure you go back and check your answers. Give it a try. Okay, the answers are in two parts. This one's all about finding V. Since I know that it's moving in a circle and it's a force acting on it, at minimum the amount of force would be the force gravity. Anything less than force gravity would cause it to fall off the rails. So I went force and said, well, my mass acceleration would be force gravity. And I went and solved, plugging in VT squared over R for my acceleration y. Mass was canceled, and I got a velocity of 9.90 meters per second. If, for instance, kind of talking about this for a second, there was more, you had a higher velocity in this, there would have to be a normal force. But because we're assuming the minimum, we're looking for the minimum value, the normal force doesn't factor. If you got all that, if your answer makes sense, good. Go ahead and try the second part or go check your answer if you've already done it. So once you found the velocity, all it is a matter of plug and chug. You have your initial energy, which is all going to be EG, and your final energy, which is going to be the EG from the height here and the velocity. I plugged in and solved symbolically. You notice the mass canceled out because it's all in the terms. But G times the height final, which is 20, because the radius is 10, which means the diameter and the height you are above the ground is 20 meters, plus 1/2 times the square root of 98 squared over 9.8 gives you 25 meters on the nose. This can be generalized to give you an exact value in an equation, if you so desire. But for now, this is your answer. This is how you do it. Anyways, thanks for watching. Have a good one.